Hello, everyone. Welcome to another episode of On.NET Live. I am your host, Cecil Phillip, and today my friend Aaron here is going to join us. We're going to learn all about publishing with Akka.NET. We're going to talk about Kubernetes. We're going to talk about distributed systems and all of that good stuff. But before we do that, Aaron, why don't you go ahead really quick and just introduce yourself to the folks and let everyone know who you are.
Sure. Thanks for having me on. My name is Aaron Stannard. I'm one of the founders of the Akka.NET project. I've been involved in writing code all over the place in it since about November of 2013. I've been primarily responsible for working on our networking systems and clustering. And I also founded a company called Petabridge. We're a consulting business and services business aimed at helping .NET developers build highly available, large-scale applications on top of Akka.NET. And so my role in the project is I'm the lead maintainer, so I'm responsible for helping organize the roadmap and running QA processes and systems. But on top of that, in my role as a CEO of a company that helps our customers, we're also responsible for putting together tooling, best practices, documentation guides, and all that stuff on how to help people be effective with Akka.NET in production. And so one of the things that we've spent a lot of time helping customers do over the past couple of years is get Akka.NET up and running in the cloud using Kubernetes as the orchestration platform for facilitating a lot of that.
Nice. So I know you've done this like a million times already. I know you're like well documented all over YouTube and different conferences, but I have to ask you the question, right? Tell me what is the 10-second elevator pitch about what is Akka.NET and like what can I use it for?
So the 10-second elevator pitch for Akka.NET is that concurrent programming is hard. And in particular, concurrent programming with state is very hard. So there's got to be a better way to build concurrent programs than synchronization mechanisms and critical regions and blocks and semaphores and all that, 1980s era stuff.
Right.
Actually, it goes even further than that. That's really like 1960s era stuff, but I digress. Actors are a little model that you can use where you model each entity inside your system as its own little microprocess. And you communicate with that process through a mailbox that is structured as a thread-safe queue. And your little actor, which represents your entity and all the entity's state, and additionally, the business logic you want to use when that state changes, processes those messages serially. So what this allows you to do as a .NET developer is it makes it very easy to reason about a large number of concurrent changes to a large number of entities, because each of those entities themselves are fundamentally single-threaded little independent processes whose state can't be modified or accessed other than by sending that actor a message. So it allows us to take really big problems and decompose them into lots of small ones that can be distributed across a network, run in parallel, easily retried and recreated when things go wrong. And it gives developers, most importantly, a understandable mental model for reasoning about how a concurrent program should be written. So you can use Akka.NET at a giant sort of cloud scale application. The largest Akka.NET application I've ever seen myself was running on about 800 virtual machines. It was a big credit card transaction processor, is what it was doing. I have also seen Akka.NET applications embedded into Xamarin applications and Unity 3D clients, and even in embedded devices that are installed in things like oil pipelines or in cargo containers. We have one customer that built an entire distributed Akka.NET system that was mounted inside a train and used for all sorts of telemetry inside of there. So we've seen a lot of things with Akka.NET over the years. It can scale up to doing big sort of cloud sort applications, which is what we're going to be talking about today. But
Right.
it also scales down to doing like IoT, mobile apps, and that sort of stuff quite easily as well.
Okay. So for me, I guess you could say traditionally, like I know how OOP works, right? I know how OOP works. I know about like the layers, right? Like we talk about software layers. There's a presentation layer and a service thing and, so on and so forth. But when I look at Akka.NET, I kind of feel like the model or the way that I have to think about constructing my software has to be a little bit different. So for people that are like, let's say you're a traditional ASP.NET developer and you're building APIs or web things or something like that, how easy is it? Maybe easy is not a good word, but how approachable is it for me to adopt and benefit from Akka.net when I'm building those types of applications?
Well, so Akka.net is basically kind of a blend of traditional object-oriented programming and some functional programming. And probably the easiest way to illustrate this is with some code.
Okay.
So I'm going to go ahead and pull up, let's see, which of our code samples do I have here? You know what? I'm going to go ahead and pull up inside this is the actual Akka.net code base itself. Akka.net's a .NET Foundation project. All
Yeah.
of the code is licensed under Apache 2.0. We have not updated our copyright headers for 2021 yet. I will get right on that.
Nice.
But here's an example of, let me see if I can grab a receive actor from one of these samples. I think this should probably be pretty good.
Okay. And when you do that, could you also bump up the font size a little bit too?
Yeah, you got it. How's that?
Yeah, that's good.
Perfect. All right. This is a special type of receive actor. It's persistent, which means this actor's state is actually going to be persisted to a database, and then it can dynamically recover that whenever it gets restarted. Persistent actors are typically used for ones that maintain critical business state. And in the event that, let's say, the process the actor is on crashes, you want to have the actor programmed in such a way where it can recover all that state and re-enter the previous state it was in before it was shut down. So actors are a combination of, let's say, object-oriented and functional style. So actors are classes in that we go ahead and we inherit from this receive persistent actor base class. I'm going to create this little custom actor here. And then I'm going to override some properties. I'm going to have some internal, let's say, collections I'm going to use. And then inside my constructor down here, I'm going to go ahead. This is where the functional style kicks in. I'm going to declare some receive handlers down here. Or in this case, I'm going to say every time this actor DQs a purchase item message, this is the type of message we're going to handle, I'm going to run this function. And so an actor can only run one function at a time because we process the content of our mailbox in serial order. We're working through the queue from the front of the queue where the oldest messages are towards the back of the queue where the newer messages. So every single time we see a message of this type, we're going to run this command. This command right here, this recover item purchased, this is how we recover data from the database when we're using Akka persistence. So this receive will only get used when this actor recovers its state after it starts. Once the actor is finished recovering its state, going forward, we're only going to use this command and any other commands we might have to process live messages that are being sent to us either by other actors or by other components of our software, like an ASP.NET controller or maybe a Kafka client, might go ahead and push messages into our actor system. Every time one of those messages gets sent to an actor, we're going to go ahead and run this routine to handle it. So that's kind of where the blend of different styles kicks in, is the fact that actors have this sort of pattern matching stuff. And pattern matching should probably be a little bit more familiar to C# developers now that we've added that switch syntax as of, I think it was C#7 where we introduced that.
Yeah, I think so.
So if you scroll down here, this is an example of an untyped actor where we don't have those typed receive statements that are declared using that generic sort of receive syntax. Instead, we have this method, this abstract method we have to override. And I'm going to switch on the message type. And for each case, I'm going to go ahead and handle it and then break and so forth. So this is another example sort of where that kind of functional pattern matching style really kicks in inside Akka. Now, it's not just the object-oriented versus functional stuff, though. That's kind of a bit of a paradigm shift for traditional developers. The other really big shift is the fact that 100% of interactivity between actors is all done via asynchronously passing messages rather than invoking functions. So the way that you might think about a traditional piece of .NET software, even one that's written using best practices, async await, and using the task and parallelism library and so forth, is those object-oriented applications are really built around method invocations and return values. And so most of the code that you write in those systems is based on, I'm going to invoke a method, and if this method is long running, I might get a task I wait on. I'm going to await on that and block the flow of execution for this particular unit of work until that dependent task I'm running on completes. And that's sort of in our Akka.NET training courses, we call that request response oriented programming. And that's something that feels so natural to us as .NET developers, because that's how all sort of say imperative and object-oriented programming has worked for the better part of, let's say, 5 decades, right? In the actor model, we flip that model on its head to some extent, where instead of, let me see if I have an example. If I go to my transformation front-end actor inside the same code set, instead of essentially receiving, actually, no, I think this is probably all right. Instead of receiving, let's say, um, a response back when we call a method, what we do instead is we send an actor a message via a tail command. It's actually what we're doing right here. If I go ahead and take a look at this backends collection, this is a list of actor references. An actor reference is a handle to an actor somewhere inside our network. In this case, this demo I was just giving to some of our customers a little bit earlier today, in this instance, that actor can actually be living in a totally different process in a different machine somewhere else inside the network, or it can actually be pointing to an actor running inside the same process that I'm currently inside of right now. And we don't really need to care. Actor references are what's called location transparent, where in the event that the actor is remote, the message we send that actor is going to be serialized, sent over the network, deserialized, processed by the actor who received it, and maybe that actor will send a response back. But I digress. The big thing I was talking about in terms of the paradigm shift is what's happening down here. What I'm doing here is in my list of backend actors, I'm kind of implementing like a poor man's round robin router right here, where based on this job counter, I'm going to go ahead and use some modulus to basically kind of evenly pick between all the different backend actors registered with me, and I'm going to send them this job. Tell command is an asynchronous fire and forget message, where I'm basically saying this class is my message. I'm going to send it to this actor. And the other thing I got to do actually, I'm going to go ahead and say the sender of this message is the same actor who sent it to me. That way I can go ahead and preserve the reply to address the best actor's going to use over here. Well, I don't get any task I can await on. I don't get a return value. I don't even know if the actor I sent that message is going to be able to receive it or not. All I know is I took this artifact, pushed it out to that actor, and I'm going to go move on to doing whatever it is I want to do in the next message I'm going to process. So, kind of mental model for working with actors isn't so much thinking about methods and return values as much as it is thinking about messages and protocols. What sort of reply can I expect back in this scenario? Well, in this case, I'm going to tell this message to this transformation backend actor right here. When I receive this transformation job, I'm going to reply back to the sender with a transformation result. I'm going to go ahead and include my full actor path. Every single actor in Akka.NET has a globally unique URI. It kind of looks like an HTTP address. We're actually using sockets for facilitating all the communication between actors inside our network, but it's gonna go ahead and have a URL structure that looks pretty familiar. I'm going to reply back to the original sender of this message with I'm going to take the original string they gave me, convert it to uppercase, and I'm going to incorporate the address of the actor who processed it. So if I go ahead and I launch this little code sample in Visual Studio here, take a little look at how this runs. This is using a little 5-node Akka.NET cluster. It's all running inside a single process. So our cluster is formed. Now all the nodes in the cluster have connected to each other. And now we're able to start exchanging messages back and forth. So this particular little demo I just fired up here, let me go full screen of Visual Studio for a second. I have a total of 5 nodes I'm launching. When I say 5 nodes, in a traditional like production Akka.NET application, one node would be equal to one process, and that would typically be running inside its own Docker container or inside its own Kubernetes pod. That's what we're going to see a little bit later with some of the other demos that I have. But I'm going to launch 2 different types of services here. One's a backend service that does the processing, the other is front end that receives the request. And so if I scroll down, my little launch backend function is going to try to grab a port number, and I'm going to pass it in for a couple of nodes here. These 2 ports are static because these are the seed nodes we're going to connect to. One of the things that we'll talk a bit about is Akka cluster and how we actually build a highly available network of actors to be fault tolerant, scalable, and resilient against all different manner of network failures. Um, Having all the nodes connected together is kind of part of the big picture there. But I'm going to start my actor system. This is kind of like the local resource for being able to spawn actors and give them addresses and mailboxes, and also to give them a dispatcher so they can actually get scheduled and execute work behind the scenes. By default, all Akka.NET actors get run on the .NET thread pool, just like how any other task would inside a normal ASP.NET or gRPC application might.
Right. So in my head, this is how I'm kind of thinking about it. So traditionally, when I think of, I'm running an app and my app has instances of these like concrete objects, and there's usually like 1 or 2 of them, but not like many of them. Right. And then they do a particular thing. Like there's an entity framework thing, and they might have like some service class of some sort and a caching thing and whatever the case is. But I'm not thinking about like hundreds or even thousands of these instances of these things. But when I look at Akka.NET, I'm imagining like an ant farm, right? And like a bunch of little ants. And individually, they're not doing a lot of work, but together, collectively, they kind of form this mesh of functionality. And now, based on whatever the task is I want to do, I'm going to engage some subset of the mesh to kind of flow information through it and get the job done. So would that be like a correct analogy?
That's exactly right. That actors are cheap resources in Akka.NET. And the other big difference that you touched on is that normally when we're building, let's say, an ASP.NET Core application, everything we think about is is sort of in this sort of transient request oriented style of programming, where I'm going to get this HTTP request, and in order for me to fulfill it, I need to run this entity framework query and get a data set back, and then turn that into a response object, and then dispose of everything when I'm done. And so you're kind of thinking about all of your application and object lifetimes in these somewhat either transient scopes for request objects or singleton scopes for objects that kind of live across, let's say, a much larger number of requests. Singleton scopes might be for things that are fairly static inside your
Yeah.
application. Well, Akka.NET flips that whole model on its head. Actors live forever. They are not request oriented objects. So this actor can stay alive and receive millions of requests over the course of many months and continue to process, fire notifications when it reacts to changes in its state. And it can go ahead and do all the same stuff you might do in ASP.NET. So, for instance, you might have an actor that's going to go ahead and periodically persist stuff to SQL Server using Entity Framework, or maybe an actor that might make a call to a web API. Or is also often the case, maybe the actor is going to go and write some output to SignalR for building, let's say, an interactive, chat room or something.
Right.
Actors can do all of these things, and so what actors really give .NET developers the ability to do in the context of, let's say, web and cloud applications, is they give .NET developers the ability to do work in the background outside of the scope of the requests they're processing. And they also give .NET developers the ability to manage state. And that's probably the real killer feature of Akka.NET Actors, is you can build things like a distributed cache or a backplane for SignalR, or maybe some sort of integration handle for being able to write messages out to RabbitMQ or Azure Service Bus. It can do all these things really inexpensively. And that's what kind of makes it interesting and powerful for a lot of these use cases. So in this instance, what I've done is I've got this little back end actor that's going to do some processing, a little front end actor, and then we're going to use a timer in Akka.NET to periodically query our front end actor and say, hey, I would like you to transform this hello plus whatever this counter is. And I'm going to use the ask operation in Akka.NET. I'm going to ask this actor this input, and I'm going to expect an output of type object back. So one of the things you actually can do with Akka.NET if you want, I mentioned earlier that that tell method on actors is fire and forget, and you're not going to get a typed response back you can await on. Well, the ask keyword, you can await on that if you want to. This is basically how you would implement request response inside Akka.net. And this is how you'd integrate an Akka.net actor with something like an ASP.NET controller, where a request comes in from ASP.NET. You want to query your actor system, have it do some work, and send you a response that you can go ahead and include in your HTTP output. The ask keyword is the right tool for doing that inside that context. So if we take a look at this, we're basically using a timer here on, I don't know, a 2-second interval. We're repeatedly querying this front-end actor. This front-end actor is going to periodically forward those jobs to the back-end when it receives them. And then the back-end actors are going to receive those jobs and reply back to the sender. And replying back to the sender is going to cause this task to complete. And we're going to be able to write this output out to the console. And let's see what that output actually looks like. So you can see here that that every single message appears to be processed twice. That's because we have two different front-end nodes both running the same bit of code simultaneously. They're both using a scheduler, and they're both incrementing the counters the same way. They're both incrementing a counter by 1 every 2 seconds. Because of the order in which all the back-end nodes join this cluster together, they all appeared in the exact same sort order inside this list right here, which is why it looks like the same node is handling every single request. I could theoretically try to break up the order using a breakpoint or something like that, and you'd see it get staggered, where hello 218 might be handled by 2551, and the second hello 218 might be handled by 2552. That's kind of besides the point.
Right.
So this is kind of the basis for like a really simple networked Akka.NET application so far, where all we're doing is just kind of using the cluster to facilitate some really simple communication back and forth between a handful of different nodes inside the system. You want to see a more sophisticated ASP.NET Core sample?
Yeah, that'd be great. Because one thing I was going to say to you is, so I've read a lot. I've read a lot of your documentation, and it's one of the things that I honestly love about your project. Akka is cool, but documentation I think is really good.
Thank you.
And as I'm reading through your documentation, one of the things that really stood out to me was the fact that the programming model for Akka feels like you can write small applications with it, but then it's something that could scale to thousands and hundreds of thousands of nodes, but I don't really have to change that much code.
No, you don't.
Because you have these things called like location transparency, and there's Akka.cluster and Akka.remote. So for me, those are like the killer features, right? Like I want to be able to build an app, and maybe it's just internal, and then there's just a couple tens of people that are using it. But then when it becomes, well, hey, we want to go big time now, we want to make this open to customers, and now we got to scale it. I don't want to have to rewrite the app, right? Like I'd love to be able to just say, let's increase the node density and just have it scale.
That's absolutely right. If you go ahead and model your code in such a way where you can go ahead and use actors to solve one instance of the problem, that's the hardest part. But if you need to solve, let's say, and by the problem might be, in this case, we're going to run this web crawler code sample real fast. In our case, one instance of the problem is crawling one domain. Well, here's the good news. This piece of code that I've written could crawl 10,000 domains in parallel if we had the computing power to do it. And I could do that without having to modify any of the source code that's in here. So if you want to go ahead and come along with this, this is in the github.com/petabridge/cluster.webcrawler repository. It's open to the public. I've got it running on my system. Go ahead and build the Docker images that you can go ahead and use to run this if you want. You just do build.command docker. Now, I've already done that, so I'm not going to bore you all with showing you that again. What I'm going to do instead is called docker compose up-d. Now, I have a Kubernetes version of all this too, but we're going to start with docker compose just because it's simple. So I have a simple network up and running. I'm going to go ahead and use a command line tool that our company produces. This command line tool is free, called petabridge.command. It's like a diagnostic tool for tinkering around with Akka.NET clusters. I'm going to go ahead and use petabridge.command to show what the current state of my cluster looks like. So I can see the internal network address inside the Docker NAT, the Docker Compose created. I can see that I've got one node running on this domain name and another running on these two. Then I've got my fourth node is running on a static domain that I specified inside my little Docker compose file on here. These properties right here are what are known as roles in Akka.cluster. Roles are how we differentiate different pieces of software or different services that are all inside the same cluster together. So Akka.cluster is fundamentally a peer-to-peer network where all of the nodes inside the network get connected together and they're all aware of each other's location on the network, and they're all aware as who is available and who is not available for work at any given time. This is one of the things that makes Akka.cluster extremely scalable, is we know where we can route traffic and where we can route work as the network grows and shrinks over time. And it grows and shrinks over time as a result of using something like a horizontal pod autoscaler in Kubernetes, or using Azure App Service autoscaling on Azure. So I have these 4 nodes inside my cluster. I can see that all of them are up. This means they're available to do work. And I can also see the version of my software that I'm running on each of these. So 3 of these applications are all built using my cluster.web crawler solution. This solution right here is a Docker image I downloaded off of GitHub. So that's why the version number is a little different there. So I'm going to go ahead and type out pbm. Petabridge.command this is the command line tool. It's a .NET Core tool you can install. And it's automatically connecting to a default port and a host name that my Lighthouse pod is bound to. So I'm going to call cluster tail right here, which will stream out some of these cluster events as the cluster changes its shape going forward. Now, the next thing I'm going to take a look at is if I go into my Docker dashboard, I should see the port number that my ASP.NET Core node is running on top of. So let me grab that. Localhost 8808. All right, let me pull that up.
I feel like that PBM command is almost like kubectl.
It is.
Just without the Kubernetes part.
Without the Kubernetes part. It's mostly for being able to query and manage Akka.NET functionality. So like other stuff I could do with PBM if I want. Actor hierarchy. This will give me a little printout of what the actors look like in my cluster. So Akka.NET actors get organized into these family tree structures where you can kind of think of it like parent and child processes. This is a parent process that spawns this child process, which spawns this child process like this. And if I killed this actor, it would kill all of these actors underneath it. So that's kind of part of the way the actors are organized. Now I can do some more cool stuff with that in just a second. The other thing I can do is I can do an interactive session on my screen real fast. Remote. I can take a look at the number of association events. I think I've got remote connections command. I can see which nodes we've connected to and so forth over the course of, well, I don't know how many. I think this stores it for up to like a few hundred events or something like that.
Yeah.
So I can get some information on the connection history. But let's go ahead and actually crawl a domain. Let's crawl petabridge.command website I just pulled up. Query that. Now you'll see this little detail right here. We have one routee. So what does this actually mean? And by the way, we're using SignalR to go ahead and pump out data out of web crawler. What's going on inside my little Visual Studio solution here, and I know it's probably a little difficult to see some of the tooling over here on the right. So I'll go ahead and see if I can zoom in a little bit. That might be a little too much.
Yeah, that's a lot of zooming.
Yeah. You gonna let me?
It's fine.
Yeah, all right. We'll just do it like this. So inside our Visual Studio solution, we have our crawl service, our tracker service, and our web service. So our web service is what we're connected to via SignalR right now. Our tracker service that sits right here is what we use to actually build a crawl index. So the web service, if I go into our program.cs right here, our web service is going to, let's see, we're going to go ahead and create, I think, our little system actors down here. Maybe go to startup.cs. Yeah, there we go. So we start up our system actors somewhere inside of here. I think it's right here we do it. Yeah, there we go. So we go and we parse our web.hocon, we create an actor system, we start petabridge.command, we also merge in some environment variables here. And then we're going to create a little router called tasker. This little router is defined in our hocon file right here. And we say, all right, in fact, you know what? This needs to go to /API. There we go. So this tasker is going to basically use a routing strategy to route to actors that live in this location of the actor hierarchy on nodes of type tracker. So that little actor is actually going to listen as new tracker nodes are added to the cluster, and it'll go ahead and add those routees to its little routing table. So right now in our cluster, we only have, if I go ahead and exit out of this, we only have 4 members right now. So one thing I can do, if I want to go to, in fact, I guess I should exit out of here real fast. I want to go to Docker Compose up scale. I think it's webcrawler.tracker service. Let me double check in Docker Compose here real fast. Yeah, tracker service.
Tracker service, yeah.
So I'm going to go ahead and scale this up to, for argument's sake, let's say 3 nodes. We're going to spin up some more Docker containers. And lo and behold, we'll see some joining events being written out here, some weekly up events, and then finally the node will be marked as fully up. And yep, there it is. And we even have a brand new leader inside the cluster, which means that someone else is now the node that's going to determine who can and can't join the cluster. But if I go back, sorry, go ahead, Cecil.
Sorry. So I was going to say, so one thing I wanted to know about that. So I love how you just spun up nodes and they kind of just found each other. You know, I mean, they're like, oh, hey, here are my brothers and sisters, right? Like, let's go have a party kind of thing.
Yep.
How do you determine? I'm guessing like there's some centralized node or thing that they can connect to discover each other, or are they doing like a DNS, MDNS thing, and they're doing like a broadcast over the network?
So we're using what's called a seed node strategy. So there's 2 ways to start a peer-to-peer network. And the analogy you kind of want to think of for this is like starting a party with your friends. There's 2 strategies you can use for actually getting a party started. The first is the service discovery route, where you dynamically look for people in a group text. Hey, who wants to go out tonight, right?
Yeah.
And a handful of nodes that are available will go ahead and respond, and you form a network together. And anyone else who wants to come afterwards can go ahead and just broadcast back out to the group text. And basically they can go ahead and join the network of people who are going out to have a good time. This is all pre-COVID, of course.
Right.
So that's the example, like the service discovery route, where you might use something like the Kubernetes service API or MDNS
or console or something like that.
Yeah, exactly. The other approach is the seed node approach. The seed node approach is where you have someone who is your buddy for going out. They're your wingman or your wingwoman, where if I ever want to get outside the house, this person is always up for it. So I'm going to go ahead and contact them, and they'll go ahead and if they're available, they'll send me a response back, and we can get going. And anyone else who might want to come out with us can go ahead and just send one of us a message, and they can go ahead and join the group from there. That's sort of how a seed node approach works, and that's what Akka.NET uses by default. So in our case, I have an environment variable I populated, Akka.TCP webcrawler at webcrawler.lighthouse, and that's because I gave this node up here a static host name.
Okay, got it.
I spelled that wrong. But I went ahead and I gave this node a host name up here. And as a result of that, all the other nodes were able to join it. In a Kubernetes environment, we do this a little differently. So this guy is going to get us into Kubernetes a little bit. This is one of my Kubernetes demos I pulled up today here, but they all kind of work the same way with Akka.NET, which is typically Akka.NET applications should be deployed as stateful sets, which is a service, a sort of a deployment type in Kubernetes that is perfect for applications that house state inside of them, as the name implies, of course.
Sure.
So in this case, we're going to have 3 replicas of our stateful set, and we're going to create a headless service, which is the default type of service that you use in Kubernetes, that is going to point at the stateful set. So there's a couple of things that make stateful sets good for stateful applications. The first one is that all nodes in a stateful set are going to have reusable and predictable domain names. And so there's a formula that a stateful set's going to use. Every node is going to have a host name that can be computed as the pod's name. This is a Kubernetes like metadata variable here, dot the name of a service, a headless service that points to them. So any node anywhere inside our cluster in Kubernetes can access one of these pods via this convention. So this allows us to predict what our seed nodes are going to be. So in this case, I only have one service type in this example, and I'm going to have all those nodes act as their own seed nodes, but they're all going to get networked together this way because all of the traffic will be port forwarded from whatever this sort of, let's say, domain name is inside the Kubernetes service down to that local pod and then received. So all the TCP traffic will be forwarded and connected properly together that way. So this is sort of how we form a cluster inside Kubernetes, is we're just using kind of a DNS scheme to do it. It's pretty simple, doesn't cost very much, easy to predict, and this does not change when you do deployments, by the way. If I go and push a new Docker image and I tell my stateful set to upgrade from petabridge.phobos.web 0.10 to 0.11, all those pods are going to be rebooted with the same domain name they had from before. So our network's still going to be cohesive even after a deployment like that.
Right. And so then you get some level of predictability in terms of like where you could find things and like where their resources located.
Exactly. And the other reason you'd want to do that, aside from being able to form like a peer-to-peer network like an Akka cluster, the other reason why you'd want to do that in a stateful context is because in stateful applications, you tend to partition data. And by partition, I mean you want to mutually exclusively assign data to different nodes. You don't want Phobos Web 0 and Phobos Web 1 to both think they own the same entity. You want them to all believe they own totally different, non-overlapping sets of entities. And so typically you use what's called a consistent hashing distribution, consistent hash distribution. In order for that to work, the identities of the nodes had to be stable. That way, when the node reboots, it still owns the same partition of the hash that it did before. So it can go ahead and just get rebooted real quickly and go back to taking ownership of that range data again. If the identities were all over the place, the hash table would keep changing and overlapping back and forth like this, and it would cause us to have to migrate data back and forth from multiple locations over and over again, which would be somewhat inefficient in the grand scheme of things.
Sure. So in that previous demo you showed us with Docker Compose, for instance, you on the command line, you did a Docker Compose up and you scaled an application, to like some arbitrary number. So with the stateful set, because the names have to be so consistent, does that mean that if I do, I don't know, let's say some nodes are up and some nodes are down and I decide to do a scale, does that mean that there's no scenario where I'll end up with two versions of like Web 1? Like I'd have, like you have Phobos Web -1. I would never have two of those. I'd always have, I'd never have two instances of Web 1 fighting for Web 1 data.
Oh, no, definitely not. No, what would happen is Kubernetes would monotonically increment the IDs of those containers and say, okay, let's say we go from 3 to 6, we would go from pod identity 012 and we would add 345 would be the next one. So that would be added.
Got it. Okay.
So stateful sets are ideal for that. You're probably still better off if you're using Kubernetes, using things like normal deployments, which is basically a replica set. You're better off using that for stateless things like web APIs and that sort of stuff.
True.
But Akka.net is very happy being inside a stateful set. That kind of jives with this whole networking model that it has.
Sure.
So with this example that we're using in Docker Compose, what I wanted to show real fast is if I go ahead and try, let's say, running another crawl here, I'm going to try crawling the same domain, which my application won't actually let you do. It'll say, nope, sorry, man. In this case, I guess it did do a little bit of stuff, but looks like we stopped pretty quick because it retrieved all of the old data from what we had before. So yeah, it basically just replayed everything that was done before. It didn't really discover any new pages when we did that. But you'll notice we went from having one routee to 3 routees when we did this. So another thing I could do is we can crawl a much larger domain. Let's do docs.microsoft.com. So I've crawled this domain to the tune of 1.6 million pages before, and I think it's still much larger than that. So if I kick this off, you'll notice that we've already discovered a couple thousand pages so far, and we've downloaded 10 or 11 megabytes. Well, one thing we could do if we really wanted to scale our system way up would be the crawler nodes, who are the ones that are actually doing all of the underlying downloading and parsing of web pages. I can go ahead and say, I want 5 crawl service instances. We're going to go ahead and spin those all up. And if I take a look inside Docker Compose and I look at one of these new crawl services, this is crawl service number 5. Get a load of this. It's already starting to go ahead and download new pages. If I take a look at, let's say, crawl service number, look at number 4 while we're at it, it's also downloading pages. So Akka.net was able to dynamically scale the work of all the downloading and parsing out to a whole bunch of additional child actors that we dynamically instantiated on this crawler node. We use a technique called a remote deployment for that, which is a little bit part of this little web crawler code sample that I'm building. So this kind of gives you a feel for how some of the dynamism inside Akka.net, how we can scale our workloads up and down. We can go ahead and add new nodes and remove them on the fly. Like if I do this again, so we're currently ripping right now with 5 different crawler nodes, all downloading from docs.microsoft.com. I can scale this back down to 1 crawler node. And you'll see my cluster is going to start indicating that nodes are exiting and leaving the cluster down here. Then we'll see some members are being removed. Yeah, there we go, member removed. Okay, so we kicked all those nodes out of the cluster, but guess what? Our download is still going. That's because in a peer-to-peer network, when you add or remove nodes, all you're really changing is the capacity of the network, not its availability. So we lost some bandwidth, and we lost maybe, let's say, some in-flight requests, but the rest of the crawl system will probably retry those and not too distant future here, because there's a big queue of pages we need to download. So we're going to go ahead and wait until we've exhausted all of those before we stop crawling. Does that make sense?
Yeah, that definitely makes sense.
Good. So I haven't actually talked that much about Kubernetes yet. That'd probably be a good thing to do.
I think we should. There might be some folks here in the chat that might be looking forward to some Kubernetes conversation.
Yeah, all right. Let's go ahead and do some Kubernetes stuff. So I'm going to go ahead and spin this all back down so Microsoft doesn't blacklist my domain name. I want access to my MSDN documentation too. And I'm going to move on to another code sample that we have here. Let me grab the link to that real fast. This is another open source code sample. This is the Akka.net cluster workshop. Here we go. This is part of like a do-it-yourself course that's available online at petabridge.com/cluster. So it's kind of a self-paced course for learning how clustering works in the context of Kubernetes. And we also do CQRS, cluster sharding, there's a whole bunch of crazy stuff in here about how everything works. What I want to go ahead and do real fast is show what a real Akka.net application might look like inside Kubernetes, and why we're using it this way, and why this is a design that a lot of big customers in our industry use. We've got everyone from like Bank of America to United Airlines using Akka.net at scale. So it's a fairly popular technology. What I'm going to do here with this sample is the exact same thing that I would do with my web crawler sample, which is I'm going to go and build all my little Docker images in the background. And I'm going to deploy them into a Kubernetes cluster in just a second. So I'm going to go ahead and let some of that run. And while we're here, I think I'll go ahead and grab one of my little PowerPoints. Wouldn't be a Microsoft program without PowerPoint, right?
It would not be.
And talk a little bit about Kubernetes and what we're going to use it for in the context of Akka.net. Here's the simplest way to think about Kubernetes. Kubernetes is an abstraction over some unit of hardware. Now, whether that hardware is actual real bare metal hardware, or whether it's virtual machines running on someone else's cloud, which is like what Azure Kubernetes service is all about, What Kubernetes is designed to do is offer you an abstraction over all that, where you know you have these nodes. Each node represents, let's say, one physical machine. And then you have the Kubernetes master that kind of sits in the middle of it. The goal behind all this is you can go ahead and tell the Kubernetes master, I want to run 3 instances of this service with this domain name, and I don't necessarily want to know which nodes they're deployed onto, but I want all the networking between those containers to work transparently in a way where I don't necessarily need to care which physical host those pods are on. That's what Kubernetes gives you, is a high degree of location transparency, fault tolerance, and resilience. In the event that one of these nodes failed, Kubernetes could rebalance your deployment onto the other remaining nodes. And that's really valuable, particularly for services that require a high degree of availability. This is what we refer to when we talk about orchestration with Kubernetes, is really this ability to go ahead and abstract over the hardware and offer a common control plane that we can go and deploy into. And the way we basically just specify to Kubernetes how we want to do a deployment, that's what those big YAML files are all about. That's how you're telling Kubernetes, here's how my application works. Here's the different resources it needs, such as I might need a service to go ahead and expose my load balancer out to the open network. I might need a volume I can mount where I can go ahead and store persistent data. Or maybe I might need something a little bit more esoteric, like I might need a container with permission to manage other containers, for instance. That could be another thing you might be able to specify as a configurable resource in Kubernetes. Now, the key terms for in trying to offer a really simple view of what Kubernetes is and does. The first term you kind of want to be familiar with is a pod. Pod's a unit of execution. Typically, a pod means a single Docker container. That's going to go ahead and be run in isolation inside Kubernetes. Now, it's possible, and actually even pretty common in some cases, for pod to have multiple Docker containers inside of it. For instance, you might have a pod that has, well, I don't know, tracing and telemetry in it. So maybe you have a sidecar container that has some Jaeger tracing or maybe some New Relic, metrics in it. But usually a pod represents one single unit of application execution. Next is a volume, which is a way of basically mounting file storage. Most pods and most applications tend to have read-only volumes where you can temporarily write to it, but as soon as that pod shuts down, you lose all your data. A node represents one physical machine, and then the master kind of represents the Kubernetes API server and scheduler. Whenever you use the kubectl or kubectl command line, that's what you're really talking to. Is you're actually talking to the Kubernetes control plane which is really the master running behind the scenes there. And so if you want to build like a full-scale Kubernetes application using Akka.NET, ASP.NET Core, SignalR, and all that stuff, typically what you're going to do is you're going to version some Docker containers that have tags on them that specify the version of the software you're going to run. And then you usually expose some of the components out to the public. So in this case, port 80, which is where we're going to go ahead and receive web traffic. And then behind the scenes, you might have a number of private containers that are running like background services. And so I'm going to go ahead and provide a demo of all this real briefly. We've finished building our Docker containers. Well, that's just dandy. Now I'm going to go ahead and cheat with a big batch script I wrote. Let's see. Oh, I thought I was going to cheat. Let's see. All in one. Deploy. Do I have a different bash script in my directory here? Ah, yes. So I do. Deploy Kubernetes services. All right. Error from server, namespaces, akka.cqrs not found. Well, now we should have one. I'm going to go ahead and just skip through all of these. This is not from Kubernetes. This is from my own batch script. I created a little 10-second delay in there. Now I'm going to go ahead and get all my namespaces from Kubernetes. Namespaces are ways of like creating logical clusters within one piece of Kubernetes hardware. Makes it really easy for you to delete resources once you're done. So
it's almost not like creating like a project.
Yeah, it's like creating a project basically.
Yeah.
So we use namespaces for separating environments. We also use namespaces for separating, like in production, we have a namespace where all of our application performance monitoring infrastructure goes. So that way, all of our other services that need to talk to, let's say, Jaeger or Prometheus, can all go ahead and say, I know that Prometheus is hosted at monitoring/Prometheus
Got it.
inside our cluster.
And Aaron, we do have one question that's popped into the chat really quickly, so I want to make sure that we address this. So Vitali's here, and he's sending us a message here from YouTube, and he's asking, is there a way to share one volume across different pods?
A way for multiple pods to bind to the same volume. It's certainly possible with read-only volumes to do that. So, for instance, in our production cluster, you can take a config map, which is basically a configuration object for Kubernetes. You can take a config map and mount that as a read-only volume. So, for instance, we store things like configuration files in some of our config maps, in particular for really complex objects like Grafana dashboards. You can have multiple instances of the Grafana front end all bind and mount that same volume. Now, as for doing like sort of multiple nodes all writing to the same volume, off the top of my head, I don't think there's anything in Kubernetes that prevents you from doing that, but you are limited by what your various cloud vendors support, for instance. So, for argument's sake, you may not be able to necessarily. Um, you may not be able to go ahead and do that with, let's say, an Azure storage backed volume if you're deploying to AKS. But it might be possible using, let's say, another off the shelf Kubernetes distribution with something like a SAN attached to it. Maybe it would be possible to have a shared volume you can pass around. So it kind of really depends a bit on the technology you're using to kind of build Kubernetes on top of. And I think it also depends a little bit on the distribution of Kubernetes you're using. So I don't necessarily know if that's something that Kubernetes explicitly supports, but I also don't know if it's something that they are trying to prevent either. Now, so let's see. It looks like I may have written my Kubernetes YAML file incorrectly. Oh no. Well, when this happens, when you get an error image pull like this, usually the best way to go about digging into it is you want to go ahead and do a kube control, specify our namespace, describe. I'm going to say pod, pass this in. I'm going to go ahead and see what happened, which is we tried pulling this image, Akka CQRS.pricing 0.16. So looks like we don't have a local Docker image that has that defined in it. So let's go ahead and take a look at what we just built. If I scroll up here a bit, we just built Docker images that were version 0.2.1. Aha. So that's where I went wrong. So I'm going to go ahead and do another Kubernetes deployment now. If I go ahead and grab this, I'm going to go down. These are my little YAML files right here. I'm going to go ahead and change the versions and all this to 2.1. 2.1. Then let's see, 2.1. And finally, 2.1. Now that I've updated all these, I can go ahead and rerun. If I scroll down to the very bottom, I can rerun my little deployment script. Scroll down to there. I go ahead and redeploy all these. That's fine. You'll notice that it says Lighthouse unchanged. That's because our deployment is somewhat immutable here. You'll notice that we've reconfigured our stateful app/pricing. This means that we've successfully told the Kubernetes master, and by the way, I'm just running Kubernetes on my local computer here. But this syntax actually wouldn't necessarily be all that different for deploying directly to a cloud-hosted Kubernetes instance. But what this means is that the Kubernetes master saw in the diff that we really have changed something in our deployment specification. In this case, it's the Docker image. So let's go try redeploying all those stateful sets. Now, if I go ahead and run my get all command again, what am I going to see? Well, I'm going to go ahead and see, in this case, we have a crash loop back off down there, some image pull back off, So let me go ahead and try querying everything one more time. See where we're at. So I see that we are at just 2 desired, 2 current, 0 ready for that replica set. And for these stateful sets right here, looks like I still have an image pool back off. What do I need to do to go ahead and fix that? Well, what I'm going to go ahead and do, because I'm lazy, I'm going to go ahead and delete my Akka CQRS namespace and recreate it. Oops. The proper way to go and fix that is to actually go and modify the deployment that's in there, but I don't have time for that right now since we've only got a couple of minutes left on our stream. So let me go ahead and try redoing this real briefly. Now that we've fixed our Kubernetes deployment. There we go. It's looking a lot better. All right. Play this. Play that. All this stuff should be able to go pretty quickly. All right. Now if I do my get all, looks like there's still a problem with my pricing web container, but my trade processor, my traders, and my pricing system all appear to be running just fine. So let me go ahead and take a look one more time at my pricing web. So what's going on with this node? Well, if I want to take a little look at it, I'll go ahead and do logs, pricing web. It looks to me like it is currently waiting. Matches endpoint set up by middleware, use routing. Looks like I misconfigured ASP.NET Core. Well, that is unfortunate, but also immaterial to what we need to accomplish here. Is that I can go and log into my little Akka.NET cluster. In Kubernetes, I'm going to go ahead and do exec on pricing 0 PBM cluster show. I can go ahead and see inside my cluster, I have a grand total of 8 nodes that are all connected together. And I can see the version of software that's running. Now, another thing I can do is I can type help pricing. Work. Let me see if I can just do an interactive mode like this. Oh boy, that's not going to render nicely. Let me go ahead and do, let's see, I have a little custom tool in there that'll let me see the changes in pricing. The way this application works is we're dynamically generating trades in the background, and we're computing the volume weighted price inside our application. So I want to take a look at real fast is I want to go ahead and take a look at the pricing CLI. There we go. This is the custom petabridge.command palette that I put together. And so I want to go ahead and grab price track. I think that's it. Yeah, okay. So let me go ahead and do PBM price track. Let's do Microsoft. This will go ahead and show you the volume weighted price as it changes in real time here, being computed by our Kubernetes cluster. I also can do one for Apple if I want. And I think I've got a number of other different ticker symbols in there. But basically, we're dynamically computing trades and measuring, based on fluctuations in the order book, what the current price is for all these different instruments. Now, what we normally show in the web application when it's not misconfigured by yours truly is we have a SignalR feed that streams the same output. That'll go ahead and show you all the different fluctuations in the order book on roughly a 10-second interval or so. On top of that, I have the ability to do things like, let's say, kill off some of my Kubernetes pods that might be hosting order book data. That order book data is automatically recovered by a new node and will pick up exactly where it left off from where we were before. So the system, in addition to being, let's say, fairly elastic, is also quite resilient. In the event that, let's say, we lose some actors in one location, we can recreate those in another. They can recover their state from a database. I think they're using a MongoDB database internally to do this, and pick up exactly where they left off without missing a beat. So those are some of the types of things you can do with Akka.NET. And then with Kubernetes, in terms of the actual business use cases for it, we're using it right now for powering SDK bin on top of Azure Kubernetes service. So we're using that to handle payments and fulfillment and running our NuGet services for being able to serve products to our customers. We also have a lot of customers in industries like e-commerce, alerting and monitoring, real-time, let's say, trading and for both equities and for things like foreign currency trading. We have a lot of customers in the sports betting industry. They use Akka.net for real-time odds computation. And then we also have people doing more fun and interesting things like multiplayer video games and Internet of Things, all using Akka.net as kind of the backbone for this real-time stream processing. And they use it usually in concert with technologies like Kubernetes in order to make it easy to orchestrate and manage and scale Akka.net up and down as the workload changes with it. So yeah, that's
That's
my
awesome.
that's my spiel.
One of the things I really like about Akka, as you're showing it to us, like, so obviously, there's tons of like great stuff we could do with Kubernetes, but I also feel like it's a great framework to build these distributed apps outside of Kubernetes. You know what I mean? And I'm one of those type of developers that I like to be able to do the same stuff that I do on premise. I want to be able to do it in the cloud, or vice versa. And I often go online and spiel about, like, certain things that we do with Kubernetes. Like, it's so hard to replicate that on the cloud, replicate that on premise, because we don't really have that same tooling for on-premise type deployments. Well, looking at Akka and particularly the stuff that you have with Akka remote and Akka clustering, and now, like, I haven't ever honestly seen the command line tool, but this looks pretty awesome too. It looks like we could take a lot of that functionality and replicate that on premise with like virtual machines and those types of things. But then now when we want to go to that cloud scale, like hardened infrastructure, like we could, tweak some buttons, so to speak, right? And then not change a lot of code or not change any code at all, but like update our infrastructure deployment settings and then put that over in Kubernetes.
Absolutely. We could go ahead and scale up and down. We can use Akka.net at large scale in the cloud. But here's the thing I really, and obviously I'm biased because I'm one of the people who made the framework.
No, biased.
But one of the things I really appreciate about Akka.net, just as a developer, because I didn't create Akka.net in order to create a business around it. Other way around. I created Akka.net to build a really large-scale marketing automation platform. And this is a tool we needed that didn't exist in the .NET space. This is back in 2013. What I really appreciate about it as an end user and as a developer who depends on it is I appreciate that I can take Akka.net with me to building those same types of extremely large-scale, high-traffic applications. But if I wanted to use Akka.net to build, like the other day, I thought about building a tool for doing really simple load testing on top of one of my ASP.NET applications. I could write a really simple Akka stream component that could do that with maybe, maybe I could do that in, let's say, under like 50 lines of code. And Akka.net just spin all that up, run all the infrastructure for me, and that's just inside a little simple command line application.
Right.
Or if I really wanted to build, let's say, Lord knows whenever I have time to do this, if I finally got around to teaching myself Xamarin or Unity, I could use Akka.net for controlling, let's say, NPC behavior in one of my little video games, for being able to go and animate and move the characters around the map in a somewhat autonomous and data-driven way. And Akka.net actually makes it really easy to express those ideas and model them. So it's a really useful tool to have in your belt as a .NET developer, because even if you don't have a good use case for it right now, when you see the signs of a place where it would fit in, you'll be glad you know about it because you can go looking for it then when you're ready.
Nice. And so for our folks that are still here with us and maybe they've never seen Akka before, or they want like some good resources to kind of get started with, particularly with like the clustering stuff. Because for me, I think that's like the killer Akka feature, right? Is to be able to do like clustering. Like what's a good place to go to kind of learn about it, read about it, and try out some of the samples?
Sure. So I've got two areas on the Akka.net on the Petabridge website that are good to look at. For learning about clustering, you should definitely go to petabridge.com/cluster. This is basically a do-it-yourself sort of learn by doing course for teaching for learning how to use Akka.net inside a cluster with Kubernetes and Docker. We're about to update this next week, so it'll be totally current with the most recent versions of Akka.net and everything else. So I would recommend following us on social media if you want to learn this. The other resource that's really useful is our Akka.NET Bootcamp, which you can go to at petabridge.com/bootcamp. This will teach you all of the basics about the actor model and the Akka.NET syntax in a series of free, like sort of 17 lessons that we email out to users. We've had something like 50,000 people take Akka.NET Bootcamp over the course of 6 years. So a lot of people have done it. I would strongly recommend that if you're interested in learning about it, this would be a really good place to start. Both of these resources are quite good. And I would be remiss if I didn't mention this. The last resource that's really helpful is the Akka.NET community itself, which is bigger than me and bigger than my company. We have a lot of great community resources here. In particular, connecting to the Gitter chat that we have for Akka.NET, there's like 1,700 people in there at any given time. And there's a lot of people who can get you answers to your questions. So I'd recommend checking that out too. But definitely sign up for Akka.NET Bootcamp, so petabridge.com/bootcamp, or our petabridge.com/cluster course. Both of these courses are free and they're learned by doing exercises. So it'll be a great way to get your arms wrapped around the actor model.
Awesome. Great. Well, hey, Aaron, thank you so much for coming on, man. This is very insightful. Again, for me, it's always great to see frameworks that we could use that don't just work only in the cloud or just work on systems like Kubernetes, but things that I could start small with and grow with. So at least then I kind of have that confidence that my skills as a developer, like I don't have to relearn the world, right? Like when I want to write bigger apps, like I could use some of the things I know and then add some additional features to it, which I think is great.
Absolutely. Akka.NET is first and foremost a methodology and a sort of way of being able to reason about the complexity of concurrent and event-driven programming. But you can graduate with that up to writing high availability cloud services if you want. Or you can have fun writing, little console applications or little IoT applications, or even writing UI apps using Akka.NET too. It works in all those different environments.
It looks like someone has a question. So we have someone in the chat here on Twitch.
Yeah.
Says, let's see, I have a problem with my English, so learning English is more difficult for me. Well, I'm sorry learning English is difficult for you, but I'm interested in continuing to learn about .NET. Okay. And so we'll just give them a moment, as they kind of type that out. But yeah, so if folks are interested, definitely go ahead and check out those sites that Aaron spoke about. I know there's also your GitHub repos.
Yep.
And I think you mentioned a Gitter chat too.
Yes, there is.
The Gitter chat is still up and available, so folks can go in there and try things out. And I guess if anyone out there is building cool stuff with Akka, let Aaron know, at Petabridge or at Akka.net on social media, and let them know what you're working on. I'm sure everyone will be interested to kind of see what you've been building with the products that they have.
All right. Well, thanks for having me on. I really appreciate it.
Sure. It's been great. Thank you, everyone. Thank you for joining us, and stay tuned. And we'll be back next week for another episode of On.NET Live. Bye, everyone. Oops, forgot the music. Hold on. There we go.